Hello, everyone. Welcome back to the AAS YouTube channel. And this is the good stuff. This is the AAS Journal Author Series. And I'm super happy to have Rich Achterberg with us today. Hey, Rich.
Hello.
How are you today?
Oh, pretty good.
What's your geolocation?
Sitting in Maryland in my townhouse near Fort Meade.
Okay, very good.
And we've been teleworking since late March.
Okay, so I take it Maryland or Goddard is still shut down?
Goddard is still shut down, which is where my office is. Maryland is shutting down, in the process of shutting down again.
Again?
Wow. Maryland had been doing pretty well, and it started getting worse recently.
Yeah, we're seeing that surge, so hopefully things will get better here soon. Cool. So Rich, what do you like to do for research?
Well, my main interest is basically atmospheric dynamics in the solar system, primarily in the outer planets, Jupiter, Saturn, Titan.
Cool.
But I've been studying it mainly through using radiative transfer to get the temperature and composition, and using the temperature and composition to infer that basically the general circulation, meridional circulation, and the atmospheric dynamics, and just in generally how the atmospheres work.
So I'm always a little curious how people got into the field that they got into, right? Given that there's so many things one could get into. So how did you get into this field?
I guess when I started at grad school in the planetary science department at Caltech, we had to do two projects, and I ended up working. One of them was working with Dave Stevenson on the interior of Uranus, and the other one was working with Andy Ingersoll trying to model dynamics of coherent vortices like the Great Red Spot.
Yep.
I ended up enjoying that and kept doing it.
Here we are. Very cool.
And then when I went to Goddard as a NRC postdoc, Mike Flazar had a project to look for waves on Saturn in Voyager iris data, and that got me into analyzing thermal infrared spectra.
Cool.
After which I got involved with Cassini.
Yay, which is going to bring us to this really lovely PSJ, Planetary Science Journal article. And for those who don't know, the Planetary Science Journal is the newest AAS journal. It's also open access, so all of the articles are gold, and so you can go ahead and get the official version of the article for free. And this one is Saturn's atmospheric helium abundance from Cassini Composite Infrared Spectrometer data. And Rich, take us away.
Okay, I guess the title kind of says it all. We're looking at the atmospheric helium abundance on Saturn from the Cassini Composite Infrared Spectrometer, which is a thermal infrared Fourier transfer infrared spectrometer. Was on the Cassini spacecraft that orbited Saturn from 2004 to 2017.
Right.
And one of the goals that was proposed when the Sears instrument was originally proposed was to measure the helium abundance in Saturn's atmosphere, which is important for a couple of reasons, but it's one of the major constraints on modeling the interior and the thermal evolution of Saturn's atmosphere, because when people first started modeling Saturn's atmosphere and modeling the evolution and the temperature, they found out they expected it would cool down to its current observed luminosity in half the age of the solar system, which was a bit of a problem. And the way around this is when you look at the details of the hydrogen-helium equation of state and the expected temperature profiles in the interiors of Jupiter and Saturn, the temperature profile goes through a phase where hydrogen is metallic and helium is immiscible. That results in the helium sort of separating from the hydrogen and dropping into the interior in the so-called helium rain. And the effect of that observationally, it changes the gravity of the planet and it depletes the helium in the outer envelope of Jupiter and Saturn. And then observing the helium abundance, it tells us how much of this differentiation has occurred and how much helium has settled into the interior, because pretty much all of the solar system formation has it forming with the protosolar helium hydrogen ratio.
So just to loop back to close the problem, if the helium rain releasing that gravitational energy then lengthens the cooling.
It adds an extra heat source and lengthens the cooling time.
Right.
And it's also possible the compositional gradients introduced can affect how the convection releases heat, and that can also slow down the cooling.
Cool. Okay.
So the helium abundance has been always a one thing, and the problem is the existing measurements that have been done by previous spacecraft have sort of been all over the place. And you can actually see that if we got on to table 2 towards the end of the paper.
Table 2, let's go to table 2. And let's take a look at it. I went past it. There we go.
And while you're finding that, in general, there's been 2 typical ways that these helium abundance have been measured remotely by spacecraft. Theoretically, the most sensitive way is you take a thermal infrared spectra at the location of a radio occultation observation. The radio occultation is where you monitor the spacecraft signal as it goes behind the planet, which gives you the refractivity, which can be converted into density, temperature, pressure through assumptions of hydrostatic equilibrium. But to do that, you have to assume a mean molecular weight. And then if you have a thermal infrared spectrum and you have a temperature profile that depends on the mean molecular weight from the radio occultation, you adjust the mean molecular weight till they match, and it tells you the mean molecular weight of the atmosphere. And then since we know it's mostly hydrogen, helium, there's a little bit of methane that for the correction. But so that basically, in theory, gives you a very sensitive way of measuring the helium abundance. The problem being there are unknown systematic errors. So we did that with Pioneer, Orton and Ingersoll from the Pioneer Jupiter Saturn. There was both a radio observation and there was a thermal infrared observation, and they got a helium hydrogen mole ratio of around 0.11, which is somewhat depleted, but not strongly so. But then Voyager went to Saturn a few years later, did the same experiment, and they've got a helium hydrogen ratio of 0.034. So extreme depletion of helium in the outer atmosphere, suggesting, there's been a lot of, and that was even more than was expected. However, then when Galileo got to Jupiter, dropped a probe into Jupiter, compared that with the Voyager results from the same thermal versus in comparison, and it was outside the error bars of the Voyager measurement. So, saying, yes, we do have some sort of systematic errors in these measurements, and they're hard to quantify.
So if there was no differentiation, what would be the helium to deuterium mole ratio?
Well, the helium to hydrogen mole ratio would be around 0.165.
0.165. Okay, thanks.
If I did the math right, it's a mass ratio of 0.27.
Yeah, okay.
But so that prompted Barney Conrath, Daniel Gauthier to go back to the IRIS data, Voyager infrared spectrometer IRIS data, and try to derive the helium abundance solely from the spectroscopic data, because there's a region between about 16 and 50 microns where the dominant source is collision-induced hydrogen absorption, hydrogen colliding with hydrogen, hydrogen colliding with helium, and a small amount from hydrogen colliding with methane. And because the hydrogen-hydrogen and hydrogen-helium collision-induced absorption have a slightly different shape, you can, in theory, measure the helium abundance that way. If it requires it's very subtle differences. So you need a fairly high signal to noise ratio and good absolute calibration.
Okay.
And they did that with the Voyager data, and then they got a number closer to the Pioneer, which is 0.11 to 0.16 again. And that's basically had been the standard number from 2000 until Cassini. But because of the discrepancy between that and the thing, and there's a lot of systematic problems in the infrared only measurements, we'll get through when I start going through my paper because I ran into the same problems. So because of all of those differences, which one is right, it was one of the main goals of the Cassini mission was to get a new number.
Mm-hmm.
So back in 2016, Cassini VIMS looked at data taken in the wake of there was a storm on Saturn in end of 2010 through 2011 that basically cleared the aerosols out of a latitude band on Saturn, and VIMS was able to look in the 5-micron band there.
Okay.
And basically they needed a fairly low helium abundance to explain, because again, there's a 5-micron window where collision-induced hydrogen is one of the dominant absorbers, although there's also some phosphine and germane lines in there that have to be modeled out. But to explain the brightness they were seeing, they needed a fairly low helium abundance.
Mm-hmm.
Otherwise, they wouldn't be seeing as deep as they were.
Right.
And then in 2018, Tommy Koskinen on the Cassini UVIS thing did this same sort of thing, comparing thermal infrared with occultation data, but he used UVIS stellar occultations from the ultraviolet spectrometer on Cassini, which gives you basically the helium, or the hydrogen and the methane mass fraction or mole fraction, well, actually density as a function of altitude up in the thermosphere. And by connecting it to density versus altitude profiles worked out from Sears limb observations, they again got numbers similar to the Conrath and Gautier or Ingersoll numbers of this high thing. So we've still got this discrepancy between slightly depleted, strongly depleted.
Right.
And so I went through and basically, I've been working on actually doing it with Sears data, both with the Cassini radio occultation data, which is not out yet, and then with the Cassini only data, which is the subject of this paper. And the conclusions you can see in this table, we'll see I'm coming down with the low end of the numbers again. So
even lower.
If we go up to, so what I did for this is, for Cassini, we did a large number of observations where we basically set our far IR focal plane. These were actually our focal planes fixed at a latitude on Saturn and just integrated for 11 or 22 hours, 1 or 2 rotations of Saturn, just sitting and staring and getting integration time, this is actually designed to look for waves, but it also gives us really good signal to noise on a zonally average temperature spectrum.
Okay.
And so figure 1, table 1, figure 1 shows, the locations, latitude, and time of all of the observations. So we had a lot of them. And by the way it looks, if you look at figure 2, this shows the sensitivity of our spectrum between 20 and 600 inverse centimeters. It's essentially half a micron at the left end and 16 microns on the right end. We work in wave number space. This is the sensitivity of our spectrum to 3 different things. The red line is our sensitivity to the assumed log of the helium abundance.
All right.
And the green line is a sensitivity to temperature, and the blue line is a sensitivity to what we call the hydrogen parafraction, which is a kind of a goofy thing to explain, but ends up becoming important in here for quantum mechanical reasons because of coupling between the spin states of the individual hydrogen nuclei and the rotational state of the hydrogen molecule. They're coupled so that if the spin states are parallel, only the even rotational states are occupied. If they're anti-parallel, only the odd rotational states are occupied. And so they sort of act as separate gases, and the timescale for equilibration between the two, in the absence of catalysis on surfaces, is on the order of a decade.
Okay.
And this ends up making the ratio, and at the cold temperatures, once you get below about 250 Kelvin, the ratio of para to ortho hydrogen becomes, the equilibrium ratio is temperature dependent.
Mm-hmm.
At high temperatures, it's 3 to 1 because the ortho states are triply degenerate, and then as you go to 0 Kelvin, everything cascades down to the lowest state, which is a para state, and so the equilibrium para fraction rises.
Okay.
And that ends up actually making the para fraction a good measure of vertical motion.
Yep, I'm with you.
But it also means it's out of equilibrium.
Yes.
And so we need to know the para ratio, para to ortho hydrogen ratio to model the spectra properly. And as we'll see in a couple of the pictures, part of the problem, you can kind of see comparing the red and the green lines, if you stick between like 200 to 600 wave numbers, it's pretty strongly anti-correlated with the sensitivity of hydrogen and the sensitivity of para fraction are fairly strongly anti-correlated.
Yep.
It decorrelates somewhat as you get out to 400 to 500. However, Voyager Sears does not have good signal to noise out from 400 to 600 for historical reasons that we don't have time to get into. Well, Voyager did. So if you to sort of differentiate that, if you go to the longer wavelengths, you can then better differentiate the helium from the para fraction effects on the spectrum. However, now you have to model in absorption from phosphine and ammonia, which is all those squiggly lines on there are phosphine and ammonia absorption bands. So if we go down, well, we can actually go down to just figure 3. And in figure 3, what I did is took one of the spectra from early on in the mission, zonal average, did a combined retrieval of temperature and para fraction for various assumed ratios of the helium to hydrogen ratio. So do a temperature and hydrogen para fraction retrieval, assuming different helium abundances, and look at how that affects the residuals. And you can see if we just use the shorter wavelength then from 230 to 600 inverse centimeters, which is what was used with the Voyager data, the spectra fit roughly equally well over a large range of helium ratios.
Yep.
If we extend it to the longer wavelengths, model out phosphine and ammonia as well, you can see the fits start to deteriorate as the helium abundance gets above 0.7, 0.8 or so. And so the fits to that are actually shown in figure 4.
Okay. Okay.
There's a bit of a complicated figure, sorry, but fitting the 200 to 600 wavelength on the left, the 800 to 600 wave number on the right. And you can see that there's a couple of gaps in there where there was noise in the instrument. And the different colors are for different assumed helium abundances. The black is the data. And then the bottom 2 figures are the raw residuals, and then the residuals smooth down to sort of reduce the point-to-point instrument noise. And you can see that, changing the helium abundance, the changes in the fits are fairly subtle.
Yes.
And you can see if we're using the 200 to 600, the differences are all around 500 wave numbers, and they're below the noise level, which is the dashed lines are the noise level in the average spectrum.
Okay.
Whereas if you extend to the outbound, we do start to see some deviations at the longer wavelengths that are outside the noise level. And we also get some larger deviations at the 500, 600 wave number end, because adding in the longer better constrains the para fraction. Basically, the information on the para-hydrogen to orthohydrogen ratio is coming from comparing the around 150 wave numbers to around 300, 350 wave numbers. So adding in the long range gives us a much better constraint on the para fraction, and then allows us to actually get a helium abundance out of this data.
Okay. Yes.
And I don't, figure 5, the next figure just shows some of the hydrogen and temperature and para fraction retrievals.
Okay.
For the two cases, and there's some slight differences in the red and the blue are the different wave number ranges. And the main thing you can see from this is that by extending the long wave numbers really tightly constrains the para fraction at around 300 millibars, which is where the spectra are most sensitive to the pair-to-ortho ratio.
Yeah, 300.
And if you just use the longer wavelength, they just spread all over, and without going with better to signal noise. Voyager Iris actually had better signal to noise than Sears, around 500 wave numbers, and that allowed the measurements from those data.
Okay.
But the other problem we run to is if you go into figure 6 is the retrievals problem is essentially ill-posed and non-unique. There are multiple solutions fitting the data within the noise level. And so we have to make assumptions. And what we do for these assumptions is sort of constrain the retrieved temperature and pair fraction to be smooth in the sense that they deviate from an initial guess. That we train them to be close to an initial guess and for the deviations to be correlated over roughly a pressure scale height.
Okay.
And how tightly we impose those constraints affects the solutions we get. And that's the purpose of figure 6 here. The horizontal axis, this is again just retrieving temperature and rarefaction for an assumed helium abundance.
Right.
So this is actually doing the full retrievals. But the horizontal axis is the initial guess on the helium abundance.
Mm-hmm.
The different colors are how tightly the parafraction is constrained to be near the initial guess, which is an equilibrium parafraction for the initial guess temperature profile.
Okay.
And then the different colors are how tightly the constraints are applied on the parafraction retrievals. And then the error bars are just the formal uncertainties due to instrument noise. And you can see that changing how tightly you can train the parafaction to the initial guess affects the retrieval by more than the instrument noise. And there is some sensitivity to the initial guess,
Yep.
which it's an inherent problem in retrievals. It always happens. And then the top part of the panel is just the chi-squareds of the fits.
Mm-hmm.
But the important thing is, I mean, if you look at sort of the middle of that thing, you get similar solutions with different helium ratios that have the same residuals.
Right.
So there's sort of this inherent problem, and you just sort of, and for that reason, I sort of punted on putting a formal uncertainty on my retrievals and just sort of do what Conrad and Gautier did with the Voyager data, say we can't really put a formal retrieval on this. We have to give sort of a range of values that are consistent with the data.
There you go. Okay.
But you can't really say this is a formal 1 sigma error bar, unfortunately. And I've thought one of the things I kind of like to do in the future is see if you could apply something like Markov chain Monte Carlo techniques to actually put something closer to a formal error bar on this. If one can come up with some sort of statistically meaningful a priori.
Yes.
There are a couple other effects that do come in on here. If you go down to figure 7, there is a slight contribution from methane to the absorption and to the mean molecular weight, which also affects the outgoing spectrum a little bit. So in this case, just shows the sensitivity to the retrieved helium to assume tropospheric mole fraction, and the gray bar is sort of the 1 sigma error bars in measurements of the tropospheric methane done by Lee Fletcher from Sears data, and it's basically has an effect comparable to the random instrument noise on our retrievals. A partially bigger problem is the effect of aerosols, because Saturn's troposphere is hazy.
Yeah.
However, we could place absolutely no constraints on the haze opacity at the long wave numbers.
Okay.
And in theory, the particle sizes determined from near-infrared imaging data are small enough that the opacity out at the wavelengths we are looking at should be negligible. And that is consistent with our data. The problem is we could put in some haze opacity and it basically has almost no effect on the residuals. So if we look at figure 8, I basically did the retrievals I put in a gray absorber in the troposphere, varied the optical depth, and did the retrievals. And if you put in a haze, it reduces the retrieved helium abundance. And putting in a slight amount of haze actually does improve the retrieval slightly, although the statistical significance of that is pretty iffy.
Yeah.
So,
okay.
Which basically means that the helium abundances in here are essentially upper limits, and if haze opacity is important, the actual helium abundances could be lower.
Okay.
And the other major source of uncertainty is what the spectroscopic parameters. Since the mid-'80s, we've generally been using hydrogen collision-induced absorption opacity data from software produced by Alexandra Borisov and her collaborators. Did a whole bunch of these, made some quantum mechanical models, sort of distributed Fortran code that calculates all these, and that's generally what's been used. However, this code does not include some dimer features that are in the center of the bands, which is during the collisions, if you get two hydrogen molecules closer to another, you get a little van der Waals bonding, and that can actually, it produces a little extra opacity in the centers of the lines that's not accounted for in their models. And there have been some newer models that try to include those. And these were finally included as an alternate data set in HyTran a couple years ago. They finally did these calculations it had originally only been done for equilibrium para-hydrogen ratios. So now that these calculations are available at a range of para-hydrogen ratios, so we can actually do the calculations for variations of the para-hydrogen fraction.
Okay.
So I went in and used both sets of hydrogen absorption parameters to do the retrievals.
Cool.
And the results for everything are in figure 9.
Money shot. Yep.
So the left-hand column is the old hydrogen absorption coefficients from the mid-'80s. The right-hand column is the latest ones. Lee Fletcher didn't actually do the calculations, but he wrote the article publishing them, and he modeled some data with them and then got them into HyTran. So he's the first author on the paper. And it's just plotted as a function of latitude, emission angle, and time, just to see if there was any sorts of systematic effects. And you can sort of see there is actually some weak trends of the more recent data having higher values than which is actually suggestive of calibration drifts or some other effects. You can also see there's some slight latitude effects, which is, suggests there may be some minor effects in either the data calibration or in the spectroscopic modeling that are not being completely accounted for. We don't see any effects on emission angle until we get above 60 degrees. And I actually cut the emission angle off at 60 degrees because I actually do see some systematic effects at higher emission angles.
And the dotted horizontal lines?
The dotted horizontal lines are basically the mean and standard deviation of the points there.
Okay. Okay.
And so those dotted horizontal lines are basically the result of the paper.
Okay. Nice.
However, and just the one other thing I did, because the results I'm getting were so much different from what Conrath and Gautier got from the Voyager data,
right, I
went back and reanalyzed the Voyager data.
Okay, good.
And basically reproduced the result, which is figures 10 and 11. So basically, there are some differences because I don't think that Conrath and Gautier had methane in their models, which would reduce the results slightly. So my numbers are a little less than theirs, and I pretty sure that's because they were not including methane in their models. And I can reproduce the results, essentially. So there is something different between the new data with Sears, the old data with Voyager, which strongly suggests there's some sort of systematic effect in here that we haven't found and aren't accounting for.
Okay. Interesting. Interesting.
So which numbers do you believe?
I
I don't know.
don't know. It's hard to say.
And
right.
the next step is I'm also working on this by doing the comparison with the Cassini radio occultation data.
Okay.
But that's in work. It's sort of, I'm still working on the error analysis. I'm still waiting for the radio occultation data to be published. Some of it has been, but not all of it has. And that needs to go out first.
Okay. So that's probably one of the first next steps.
So the first next step is to get the paper on combining the Sears and radio science data.
How about on 5-year timescales? Where does this go? How do we resolve this this discrepancy or next steps? Are there new missions coming out? Are there proposals for new missions? Are there additional theories?
I mean, a Saturn probe is one of the potential. It's one of the missions that is in the planetary science decadal as a potential New Frontiers mission.
Okay.
And given all of these inconsistencies between the different data sets, the fact that there are systematic uncertainties that we don't understand, I actually do now think I understand some of the systematic uncertainties in the very low Voyager number. And that'll be discussed in the next paper.
Cool.
But
look forward to seeing that paper.
I really think the only way we're going to get a number that everybody will agree with is to send a probe with a mass spectrometer that's well tuned for mass 2, mass 4, mass 3.
Okay. Drop it.
Drop it in and measure it in situ.
There you go.
That's the only way you're going to get a number that somebody can't argue with.
Well, let's hope that happens sometime in the next.
I would like to see that happen for lots of reasons, but
yeah.
getting all of the noble gas abundances would be
that would
very important for people doing interior modeling.
Definitely. Very cool. Very cool. Nice piece of work. Rich, I want to thank you so much for sharing that lovely article with us. Okay,
thank you for inviting me to do this.
Oh yeah, my pleasure. It's a great article. It caught my eye, and of course, hydrogen helium is a big thing in the planet. So yeah. Yeah,
it's a paper a few people have been waiting for a long time. And unfortunately, Barney Conrath passed away from lung cancer before he could get it out himself.
Oh no.
And I ended up inheriting the problem from him because it was much more difficult than we expected.
Mm-hmm. Yeah, as your article shows. So what sort of a timescale are you expecting your next one to come out, your next paper on this?
Hopefully get it submitted by next spring.
Okay.
I kind of need to because the funding supporting this is only runs through next spring. So
okay, cool.
I mean, I just have to do a little more error analysis and then write it up, and then wait for the the data, the radio occultation data to be published so I can actually submit it.
Right. Okay, very good.
But hopefully in a few months, and hopefully we'll be out next year.
All right. Well, I look forward to that, and maybe we'll do another one of these. All right, everyone. Thank you so much, and we will see you on the next one. Bye-bye.
Bye.